Hi there, welcome back to Real Analysis. In this video lecture, we're going to talk about the material in section 1.7 from our text, and it's the Archimedean property, the real numbers. So on this opening slide here, I've got a picture drawn of the real number line. It's kind of the usual, and what for us will be the only way that we visualize the real number line. It's the set of all numbers on this horizontal line. And then I've marked on there the natural numbers. The natural numbers are, of course, the counting numbers starting at 1, so 1, 2, 3, and so on. And they're equally spaced apart by 1 unit on the real number line. And certainly, just looking at the picture and using the definition of the natural numbers, you'll agree that the number 1 is a lower bound for the natural numbers. Every natural number is greater than or equal to 1. In fact, 1 itself is a natural number, so you could even say something better than a lower bound. 1 is actually a minimum in our technical sense because it's a lower bound that belongs to the set. So it's a minimum, and in fact, it's the infimum. It's of all the lower bounds of the natural numbers, 1 is actually the greatest lower bound. So it's the infimum of the set of natural numbers. You could probably just kind of pass over without any proof at all the following fact that the set of natural numbers, unlike being bounded below, it's not bounded above. So there is no real number out here, alpha or whatever you want to call it, that is greater than or equal to all the natural numbers. Right? So that if you give me some real number alpha, it's always possible to find some natural number n that's going to be greater than or equal to that real number alpha. That's just a more precise way of saying that the set of natural numbers is not bounded above. Kind of seems like a trivial statement. It's a little bit surprising. I don't know, it depends on what surprises you, that you cannot deduce this fact only from the field and order axioms of the real numbers. So you need that completeness axiom. You need the fact that every bounded set of real numbers, say bounded above, has a least upper bound in order to deduce the fact that the natural numbers are not bounded above. So that's our purpose of this lecture, is to produce or to give a proof of this fact. And it's usually called the Archimedean property or the Archimedean principle of the real numbers. So I'm going to scroll down a little bit and show you the statement of it from our text. And also you can use the text numbering system if you want to refer to this. It's theorem 1.111, but I probably won't remember that number, but so I'll just refer to it by its name, the Archimedean property of the real numbers. It's stated slightly differently here than what I wrote in my handwriting above, but I mean the same thing, that the set of natural numbers has no upper bound, or as I've written above, the set of natural numbers is not bounded above, right? So that's the main goal of this lecture, is to establish a proof of this. And as I alluded to, it's going to rely on the completeness axiom. Before we launch into the proof, kind of the crux of it, if you like, is a certain fact that I've cut out here and called it a lemma. And this is actually going to be a useful tool for us when working with supremums. So I've decided to state it here as a lemma. I'm not numbering it because it's not in your book in the numbering system. So inside of this lecture, we'll just refer to it as the lemma. And then it will become one of our working tools. But what does the lemma say? It says if you take a non-empty subset of the real numbers that's bounded above, so I'm calling that subset E. I've written that it's not the empty set, it's a subset of the real numbers, and the hypothesis are that it's bounded above. So it has at least some upper bound. And because of the completeness axiom, if it has an upper bound, it's got a least upper bound, it's got a supremum. So I'm going to denote the supremum by the letter U. Then the lemma says that for every positive number epsilon, this is the Greek letter epsilon, for every positive number epsilon in the real numbers, you can always find an element of the set E that will be bigger than U minus epsilon. All right, so said another way, if you subtract any positive quantity from the supremum of a set E, you can always find an element of E that's bigger than that result. All right. And not to give away the proof now, but why is that? Well, if you subtract a positive number from the supremum, you get a number that's less than the supremum. And because the supremum is the least upper bound, any number that's less than it cannot be an upper bound. And if you're not an upper bound, well, yeah, I'm I'm launching into the proof here. Let me sure I've written it out here. I'll just kind of narrate it. You maybe have to stop and write this statement down if you're trying to take notes from the video. I'm just going to scroll to the entire proof. Ignore that horizontal line there. That's just where the break in my electronic paper is. So using the notation above, um, given this set E, and I've got its supremum U, like I was saying in kind of the preamble to the proof, if epsilon is positive, the number U minus epsilon cannot be an upper bound for E if epsilon is a positive number. That's because U minus epsilon would be less than U. I'm not going to delve in and cite sort of every one of the axioms, but this follows from the order axioms. Right? If epsilon is positive, then its opposite is less than 0. You can add that to both sides of the equation. You can add u to both sides of that and so on. So we're going to kind of use those elementary facts about inequalities. If we stop and try to sort of axiomatically cite everything, we'll spin our wheels and won't get anywhere. But this is clearly true, that if you subtract a positive number from a real number, you get something less than it, right? So why can't u minus epsilon be an upper bound then? Because, well, u is the least upper bound. Anything smaller than it cannot be an upper bound. All right, but now I'm just drilling down into definitions. If something is not an upper bound for a set, then there has to be something in that set, very important, that there has to be some element of E that is not less than or equal to this thing that is not an upper bound, right? Because if it wasn't the case, if x were less than or equal to u minus epsilon for every x in E, then u minus epsilon would be an upper bound by definition. So if you're not an upper bound, there has to be something in the set that's not less than or equal to u. And not being less than or equal to u is the same as you're strictly bigger than it. So there has to be some x in E that is strictly bigger than u minus epsilon, okay? That's the proof. That's what I wanted to show. Maybe I should have put this little picture above. It's kind of a useful thing. It's kind of the picture that I keep in my mind when I'm thinking about supremums. So I've got the set E here. It's kind of drawn as that thicker black line. The real line is visualized here. So E is a subset of it. And U is supposed to be the supremum of this set E. So the idea of my picture here is that if you subtract anything from U, that is, you look at any number less than U, because that number can't be an upper bound, there has to be something bigger than it that's still in E. All right, and you can kind of visualize this here. My epsilon is the length of that blue line, but you can take epsilon to be any positive number. If you back up infinitesimally, as they say, from the supremum, there has to be an element of E that's bigger than U. Okay, so that's the lemma. All right, so let's take a look at the proof of the Archimedean property. Remember, what we're trying to show is that the set of natural numbers isn't bounded above, and we're going to prove it by contradiction. Proof technique of contradiction, what does it mean? It means you start out by supposing the opposite of your conclusion. So if we're trying to show that the set of natural numbers is not bounded, well, the negation of that is suppose it is bounded. So let's suppose that n is bounded above. Okay, set that's bounded above by the completeness axiom has a supremum, so I'm going to let U denote its supremum. So I'm looking for a contradiction from this, so use the supremum. Using our lemma, I'm going to take the positive number epsilon to be 1. All right, so the lemma says that there has to be some element of our set, some natural number in this case, that is bigger than U minus 1. I've subtracted a positive number from my supremum. And using the properties of inequalities, that's equivalent to saying that U is less than n plus 1. But n is a natural number. It's written right here. You increase a natural number by 1, and you also get a natural number. So this is our contradiction, right? Because if n plus 1 is a natural number, it's supposed to be less than or equal to U because U is an upper bound. It's the supremum. But we've written that it's strictly strictly bigger than n plus 1. So those two statements together can't simultaneously hold, so that's our contradiction. Why did we get a contradiction? Well, because we assumed that U was bounded above. That n is bounded above. So we've shown that it's not bounded above. That's the Archimedean property. Nice. There's some consequences of this. I'm not going to prove them here in this video lecture. I'm hoping we have time to talk through some of them in the in-class lecture. The first one is actually absolutely obvious. So three consequences of this Archimedean property of the real numbers. The first one is the following, that if you give me a number x in the real number line, there's some natural number that exceeds it. All right, so given any point on the real number line, there's a natural number that's sort of further to the right of that point, if you like to think of things geometrically. That really is literally just a rephrasing of the statement that the set of natural numbers is not bounded. That no real number x could be an upper bound for the natural numbers. So we don't really have to discuss that later, it's clear. The second one, I'm going to kind of ask you, if you watch this before class, see if you can kind of modify the proof that we gave above. You'll have to put in some creativity into it, but you can kind of basically prove this second statement thinking along the lines of the first of the way we proved the Archimedean principle, or that said another way, you could just use the Archimedean principle to do it. But it says the following, that if you give me two numbers, both of which are positive, then there has to be some natural number that the natural number times x will exceed y. All right, so the way I like to think about this thing, I'm going to just sort of draw a little picture as we talk. Maybe here's my real number line. I like to visualize it. Maybe here's the number 0. X is right here. Without loss of generality, I'm going to assume that x is less than y in my picture, although it certainly doesn't have to be. If x is not less than y, you can take the natural number to be 1, and you're done. But what this thing is saying is that you can count by x's and eventually pass y. Yeah. So what do I mean by that? If I kind of gave myself a little segment to work with here, the distance between 0 and x is the size of x. And so I'll try to just sort of make this thing somewhat visually reasonable. Maybe if I zoom in a little bit, my tool will work a little bit better. No, it's not letting me do it. There we go. So I can take another copy of that, put that thing right there. So what would this number be? Well, that would be 2x's. And I won't bore you with my bad iPad skills and keep making this worse, and so on. Maybe 3x's might end up being somewhere like right around here. And then 4x's would be right here. So, we could take n equal to 4 in my picture. So this second consequence is kind of literally saying that if you start with two positive numbers, x and y, and you quote unquote count by x's, you'll eventually exceed y. X and y can be arbitrary, right? So we can talk about how to prove that in class. You can prove it beforehand and just tell me about your proof. The third consequence, really, it's just sort of a reformulation of the second one, and we'll use this a lot. It'll be an important idea for us, but given a positive number x, you can always find a natural number whose reciprocal is less than your positive number. All right, so that's sort of said another way. The reciprocals of the natural numbers are all positive, but they get arbitrarily small, if you like. They're less than or equal to any pre-specified real number x, positive number x. Okay, so I'm not going to go into the details of those things, but we'll just talk about them like that here. I'm going to end this lecture, it's not too long, with just kind of a remark about our lemma. Remember our lemma that we started with said that if you subtract a positive number from the supremum of a set, you can always find some number that's bigger than that result, a number in your set. Okay, but that lemma is actually, and this is important, it's actually an if and only if statement. All right, so let me sort of state that more precisely. If you take some real number u, and it's an upper bound of a set E, so E has to be a set that's bounded above, it's implicit, then that number U is the supremum of E if and only if the condition of the lemma holds. That for every epsilon, here I'm writing it in kind of the predicate calculus, if it's a supremum if and only if for every epsilon you can find an x in E that exceeds U minus epsilon. All right, so I'll just kind of say in a foreshadowing way that a lot of times in this course, we're going to want to prove some statement like prove that U is the supremum of some set E. And this condition on the right is how we're going to get it done. We're going to show that no matter what epsilon is, if you subtract it from U, you can always find an element of E that's that's bigger than your resulting u minus epsilon. So the only number u that can have that property for every epsilon is the supremum.